Okay, so for separation processes too, we'll start by talking about liquid extraction or solvent extraction. Okay. So with solvent extraction, we are looking at the relative solubilities of materials in different liquids. And yes, we're talking about how well a material would be able to dissolve in one liquid over another, right? And that's going to help us in our separation. Now, one thing is that we need to that the liquids that we want to consider, we don't want them to be things that are going to be too miscible, otherwise it's going to defeat the whole purpose of the separation. So we can have them being miscible to a certain extent, but we don't want them to be too miscible, right? And there are some cases where we consider that they are not miscible at all. The two liquids you are using are not going to get mixed at all. So what we can say is that we have a certain solution A, and we'll see a diagram of it very soon. So we have maybe a certain solution A that contains some solute material. So the solute material is B. And we add a certain solvent, so that becomes solution C. Right? The two of them are immiscible, they won't mix with each other. But we can shake the system, we can stir, we can cause some form of agitation so they end up being mixed up. So let me use a diagram to show this. So here the green solution is solution A, the solute is B, and then the yellow solution is solution C. That's going to be our solvent. So when we mix the two of them, when we shake it, agitate the system, they would end up mixing. But because they are immiscible, when we leave the system for a while, they will settle and separate. Now, what's going to happen is that some of the solutes that was dissolved in the initial solution A will end up being dissolved in solution C now, and that would come out as what we call the when we are done, we can separate the two solutions, and the one up here, what's going to come out, or let me say the solvent with the extracted solutes becomes the extract phase. The initial solution, what we call the carrier or feed, especially when we are dealing with flow, or the feed solution, right? That's with the unextracted solute becomes the raffinate phase. So with the solutes that didn't get extracted, that unextracted solute and the carrier solution become what we call the raffinate phase. So the extract phase is just the solution we are getting that is consisting of the solvent and the extracted solute. And the raffinate is the solution we are getting that is consisting of the carrier solution. That's what was initially holding the solute and the unextracted solute. So these are the few definitions that we consider. The extract we said is a liquid phase that is coming out, so that is exiting. And it's a mixture of the solvents that we used and the solutes that was extracted. The raffinate is the liquid phase that is exiting, and it consists of the carrier liquid and the unextracted solute. So we can have a block diagram to show this, and we can have our pure solvents coming in. That's over here. Sorry. We can have our pure solvent coming in here, and we can have our carrier with dissolved solutes coming in here. What's going to happen is that the two of them are going to end up being mixed in this system. They're going to come into contact with each other, and then the solutes would end up being some of the solutes end up being dissolved in the solvent and will therefore be extracted. So the solvent will come out with some amount of extracted solute, and the carrier will come out with the rest of the solutes that did not get extracted, right? So this becomes the raffinate stream, and then this stream up here becomes extract the extract stream. Another definition that we need to pay attention to is what we call selectivity. So when we are dealing with liquid extraction and we are talking about solvents, we are talking about, and we are saying selectivity. We are saying that selectivity is the ability of the solvent to select or choose, preferentially take one component over the other. So you see the expression, they will say the preferential uptake. So like it prefers to take that component over the other. The reason why I'm saying this is because there's a possibility that when our solvent, right, mixes with the carrier solution, there might be some extent of miscibility. So we might have some of the carrier solution being taken up by the solvent. In that case, the solvent is going to end up dissolving some of the carrier solution. So it's as though the solvent is dissolving the solute, but it's dissolving an amount of the carrier solution as well. So what we want to do is that we want a solvent that would dissolve more solutes than it would dissolve any other component. So that's what we mean by selectivity. And in this case, the other component that is present is the carrier solution itself. So we use this notation for selectivity. This means the selectivity of B over A. That's the selectivity of the. Remember we said A was a sorry, A was a carrier, B was a solute, and then C was a solvent. So the selectivity of B over A, we are seeing that the selectivity of the solute over the carrier, right? And YB is going to be the mass fraction of solutes in the extract. XB is the mass fraction of solutes in the raffinate. YA is the mass fraction of carrier in the extract, and XA is the mass fraction of carrier in the raffinate. So, um, I think let me use this diagram. What we mean by um, YB, we are saying that we are looking at the extract solution and the raffinate solution. To be able to tell how well the solvent separated the solute, we want to see how much solute was here. So we use Y for the solvent and the extract stream. So we want to see how much solute came out with the extract as against how much solute was left in the raffinate, right? So that gives us the first part of the expression, the YB over XB, or that gives us the YB and then the XB. Then remember we said that there's a possibility that, especially if it's not totally miscible, that the carrier can be dissolved in the solvent. So you might have some amount of carrier, so the fraction of carrier in the extract, some of the carrier might end up coming out here, right? And as against the amount of carrier that is left in the raffinate. So that would also be YA and then XA. Now, if we have a higher selectivity of B over, these are the same things we spoke about earlier, all these things. So we'll not have to take too much time there. But if we have a higher selectivity of B over A, it means that the solvent will take up more of the solute instead of taking up more of the carrier solution. So we'll end up dissolving more solutes than carrier solution. Now, there are a few things that we also need to take note of. Remember, we said this was the formula for selectivity. We can actually simplify this. So before we get to this point, what's happening is that if I take just the numerator, it's YB over YA. And now it's dividing the denominator, that's XB over XA. So I can actually reciprocate so that I have it to be times XA over XB. And that's what we see over here. We can simplify this further. So everything with B on one side. So YB over XB, so that's the YB here and the XB here, times XA over YA. So that's XA and YA. Now, the reason why we are doing this is because when we have Y over X, remember we said Y is what is happening in the extract phase, and X is what is happening in the raffinate phase. So when we have Y over X, it gives us a new parameter that we call the distribution coefficient or the partition coefficient. And that is just a measure of the amount that is coming out in the extract over the amount coming out in the raffinate. Right, so that gives us the partition or distribution coefficient. So that's what is being explained over here. Right, so for solutes B, the YB over XB will be equal to KB, which you can see over here. And for the carrier, the YA over XA is also KA, but now we have it to be rather XA over YA, the reciprocal of that, right? So this, when we have it in this form, we have what we call the relative selectivity. So the selectivity based on or the selectivity of the solute relative to the carrier, right? Now there's an implication from all of this. So this formula is implying that yes, there's a possibility that the carrier, some of the carrier solution might end up in the extract stream, right? Which means that it is partly miscible with the solvent. So that's this point down here. So in a case where it is not miscible at all, then it means that no carrier is going to come out with a um, extract stream. So that means from this diagram over here, you're not going to have any carrier coming out. So the YA can go to 0. So we won't have YA in there. So if YA becomes 0 from the formula over here, if YA becomes 0, then we have YB over XB times XA over 0, which is giving us something approaching infinity. So we are going to have an infinite selectivity. And what this means is that the solvents that we are working with is going to end up dissolving just the solute. It's not going to affect the carrier at all. Right? So the selectivity with respect to the solute or the solute over the solvent, since it's infinite, it means that it's going to dissolve just the solute and wouldn't affect the carrier at all. Now, there's another parameter we call the extraction factor. The extraction factor is looking at the extent to which the solute is extracted. And for this one, we are considering the amount of solute that is in the volume of the extract. So the amount of solute in the volume of the raffinate. So this is closely related to the distribution coefficient. Consider the distribution coefficient was the mass fraction of solute in the extract to the mass fraction of the solute in the raffinate, right? But now this time we are considering it with the volumes of those streams as well. So with the volume of the extract and then with the volume of the raffinate, right? So V here is the volume of the solvent and L is the volume of the carrier. Now the reason why, okay, I think we'll talk about this as we go along. So let me just hold on. So this is equal to extraction coefficient. So the y over x is the same as the kd, then v over L. So I'll explain why I'm saying that the volume of the solvent is the same as the volume of the extract. The volume of the carrier is the same as the volume of the raffinate. Okay. Okay. So I think I can talk about that here before I go on. Um, we are come to look at single stage extraction, and there are a few assumptions that we make, or there are a few assumptions we can make to simplify our question. So the first assumption I'll talk about is not on the slide here. But the first assumption is that we are dealing with a dilute system. Now, if it's dilute, what it means is that let me use no, let me not use this diagram. I think I have to go further. Okay, let me use this diagram. If it's dilute, what we are saying is that we have here a flow rate for the carrier. So this is our carrier solution. This is our solvent. This is our raffinate. And this is our extract. We have a certain flow rate of the carrier solution. In the case where it is dilute, it means that the presence of the solute is not going to affect the flow rate or the volume of the carrier solution. Please do not mistake the carrier solution for the mixture of both the liquid and then the solute dissolving. The solute is separate, the carrier itself is separate. So you're assuming that the carrier solution, that's the L, sorry, the volume of the carrier solution, that's the L, is going to be the same throughout, because even though we have an amount of solute in there, it's so dilute that the solute is not going to affect the flow rate. That's if you're working with flow, it's not going to affect the flow rate. And if you're working with volume, it's not going to affect the volume. In the case where it is concentrated, we need to cater for the flow rate of the solute as well and the volume of the solute as well. But here's the case where we are considering a very dilute system. So the flow rate of the solute and the volume of the solute will not affect the flow and volume of the carrier. So the volume of the carrier and the flow of the carrier is going to be the same as the volume and flow of the raffinate. That's the assumption we are making, because the presence of the solute is not going to change that volume by so much, right? The same thing goes with the solvent. So you're assuming that the volume of the solvent, that it's going to the amount is going to extract is not going to affect its flow significantly or its volume significantly. So the volume of the solvents that we are sending in is going to be the same, um, or the flow rate of what's coming is going to be the same flow rate of what is coming out, right? Yes, that's if you're dealing with flow rate. If it's volume, definitely the volume of the solvent coming is going to come out. Now that's also going to hold, not just because you're assuming it's dilute. The dilution one actually affects the flow rates more. But when we look at just the volumes, right? We can use the miscibility to even support that fact. Because in the case where maybe our solvent ended up being mixed with the carrier, what it means is that some amounts of the carrier can come out in the in the extract, sorry, and some amounts of the solvent can end up coming in the raffinate. So in that case, the volume of the solvent here will not be the same as the volume of the solvent here. And the volume of the carrier here, because it's possible that some of it might come out in the extract, it wouldn't be the same as the volume of the um, raffinate, right? So when it is dilute, then it means the flow rates are not really going to be affected by so much. And when it is sorry, and when it is immiscible, then we can also say that the volumes are um in quotes conserved. So yes, you are dealing with immiscible solvents, right? You are dealing with immiscible solvents. You're seeing that in the case where our solvents are even slightly miscible, it's possible to have some of the solvents in the raffinate, and we'll have some of the carrier in the extract. I think we spoke about that. For the calculations we are about to speak, we are going to assume that the solvents are totally immiscible. They won't dissolve each other at all. And in the raffinate, we are not going to have any amount of solvent. In the extract, we're not going to have any amount of carrier. So in the raffinate, you don't want to have any solvent, and in the carrier, we don't want. So in the extract, you don't want to have any carrier. So that means that from this point here, in the extract, all the solvent is going to come out. So since none of the solvent is going to come out in the raffinate, it means that all the solvent is going to come out in the extract. And for the last point here, I'm saying that in the raffinate, all the carrier solution comes out. So since none of the carrier solution is going to come out in the extract, it means that all the carrier solution should come out in the raffinate stream. So those are the assumptions that we are working with. Okay, so as time moves on, we'll deal with multiple stages. We'll deal with impure solvents, we'll deal with solutions that are partly miscible. But for now, we're dealing with a single stage. We are dealing with immiscible solvents, and we are dealing with a pure. We are dealing with immiscible solutions. We are dealing with a pure solvent. So let me talk about the pure solvents a bit. Now, you could have a case where our solvent isn't pure. So when we say our solvent is pure, it means that there's nothing else coming in with the solvent. So this is what I mean by that. Let me use an example to explain that. We might have maybe our solvent to be water. So water might be flowing in, and it's just water. There's nothing else coming in there. So that's a pure solvent. But we might have a case where maybe water is removing CO2, right? But the water that is coming in contains some amount of CO2 itself. So there's an amount of CO2 here. In that case, it's not going to be pure. So the Y naught, that's the fraction of the solute in the solvent, will not be zero. So Y naught will not be zero. But in the case where it's a pure solvent, then Y naught can be equal to zero. So this is going to be impure, and this is going to be, sorry, pure. Okay. Now we can do a balance on the entire system. So let me clear this and talk about that. We can do a balance on the solute. So we can look at the amount of solutes coming in to the amount of solutes coming out. So let me label the streams as stream 1, stream 2, stream 3, and stream 4. I can look at how much solute is coming in with stream 1 plus how much is coming in with stream 2. And it should be equal to how much is coming out. So I'm going to assume that there is no reaction, there's no generation, consumption, there's no accumulation, none of that. So that's all I'll have is my in is equal to my out. Now, if I want to determine the amount coming in, it's going to be the total flow times the fraction. So for stream 1, it will be L times X naught. For stream 2, it will be V times Y naught. So that's the flow times the fraction. Stream 3 is going to be L times X, and stream 4 is going to be V times Y. But remember, we said we're dealing with a pure solvent, so Y naught is 0, so this can go to 0. So we'll actually see that here. So if we consider a balance on the solute, the amount of solutes coming in should equal to the amount of solutes that's coming out. So no generation, no consumption, no accumulation. We are not having a reactive system, and we are assuming it to be a steady state. Right, so those are some other assumptions you can also make. So the amount of solutes coming in, we said was Vy naught plus Lx naught, which we have here. And the amount of solutes coming out is Vy plus Lx, which we have here. Now, we already spoke about the fact that the flow rates of the solvents and carrier are not changing, so I think that is fixed. We have equation 1 now. This is the balance. But we started dealing with a pure solvent, so Y naught is 0, so this can go to 0. So that we have equation 2 instead, right? And now I can make Vy the subject, so that I have Vy to be Lx naught minus Ls, and I can factorize L out to have the expression in this form. Now what you want to do is that I have my Vy to be equal to my L, x naught minus my x. I can divide through by L, so that I have Vy over L to be equal to x naught minus x. Now I can divide through by x as well, so you see why we are doing this very soon. When we do that, this becomes x naught over x minus x over x, or x naught over x minus 1, which we see over here. Now this is equal to the extraction factor because we said the extraction factor was kd v over L, and we said kd was y over x v over L. So we see this in here. We see our y over x, we see our v over our L. Now remember we did the balance for the solute, so it means the y and the x here for the solute. So there's no specific need to write maybe y subscript b or x subscript b, but you can decide to if you want to. You can make it v over L, then maybe yb over xb. So I know that you're dealing with the distribution coefficients for b, but it's the same thing. So v times y over L times x will give us the extraction factor as we spoke about earlier, right? So I think that was over here. Yes, as spoke about earlier over here. Okay, so the other thing we need to consider is the point here. This is a very important point. So sometimes you might be asked to determine the fraction of solutes that is not extracted. Now, let me go back to this diagram. I think this diagram will help us with that. So let me clear the screen and then we'll talk about that. Looking at the fraction of solutes not extracted. Now, the amount of solutes that was coming in the entire system was X naught. That was with the carrier. The amount that came out that did not get extracted was X. If you want to find the fraction that was not extracted, it will end up being X over X naught, right? So that's what it's going to be. This expression is very important to us. Now, if you want the fraction that was extracted, it's going to be 1 minus what was not extracted. So 1 minus the unextracted fraction. So that's going to be 1 minus x over x naught. Now, it's just going to be the fraction of what was coming out in the raffinate divided by the fraction of what was coming in with the carrier. So keep that in mind because we'll need it, especially when we move to multiple stages. So we are saying here that if we want to determine the fraction of solute not extracted, we can find the ratio between the solutes present in the raffinate, that is x, and the solutes present in the feed, that is x naught. So this will tell us how much solute was left in the raffinate after extraction, and this is equal to x over x naught. So we can make x over x naught the subject in equation 5. So with equation 5, we had x naught over x minus 1 to be equal to e. So that's what we have here. If I make x over x on the subject, I'll end up having equation 6. So all they did was x naught over x minus 1 is equal to e. So x naught over x is equal to 1 plus e. Then they reciprocate both sides. So x over x naught is equal to 1 over 1 plus e to get equation 6. Okay, so the fraction that um, was not extracted or the fraction that was not recovered. So sometimes they use extracted and recovered. So a fraction that was not extracted or not recovered is going to be expressed with equation 6. And the fraction that was recovered or that was extracted will be 1 minus what was not recovered. So that will give us equation 7. So here is 1 minus x over x naught. So it's 1 minus, we said x over x naught was this expression. So 1 minus 1 over 1 plus e. So you can actually work it out, but the LCM will be 1 plus e. And then if we simplify, we'll have 1 plus e minus 1. That's where the e over 1 plus e is coming from for equation 7. Okay. So we have an example over here. Here we've been told that we have 50 ml of an aqueous plant extract buffered to a pH of 8 and it's extracted with pure octanol. We want to calculate the volume of octanol needed to extract 98% of compound due to the octanol phase. We've been given our partition coefficient at that pH. Now, one thing to notice, or one thing to do is to determine what our solutes, so what our solvents and what our carrier streams are going to be, right? Now, we said that we had a long expression here, so all of this was extracted with. So the fact that it was extracted with something means that this is going to be something involved in the carrier. So this is going to be the um, carrier. So I'll represent aqueous plants extracts with APE. This is going to be our aqueous plant extract. And it was extracted with octanol. So what is doing the extraction is octanol. So octanol is the solvent, right? Okay. Now, one thing is don't get confused with the word extracting and think that this is supposed to be something relating to the extract. What you are saying is that there was a plant that they extracted something from. So they took something out of the plant. Now that solution that they took out of the plant, they want to perform an extraction on that solution. They want to remove a solute from that solution. So the solution, the aqueous plant extract is actually the carrier. It has nothing to do with the extract. So when you see things like this, don't get confused, right? And then the octanol is what was doing the extraction, so that becomes the solvent. Now we are going to assume it's dilute. We are going to assume that they are immiscible. So the volume of our carrier is going to be the same as the volume of our raffinate, and the volume of our solvent is going to be the same as the volume of our extract. If we want to find that volume, the V, we want to find the volume of our solvent. So we can start we can list out all our parameters. So we have our KD, we have the volume of our raffinate, we don't know the volume of our solvent, that's what we are looking for. Now we're told that the volume or the fraction, sorry, of the solute that was extracted. So we said 98% of the compound B, that's the solute, was extracted to the octanol phase. So the fraction of the solute that was extracted was 0.98. So the fraction not extracted is 1 minus 0.98. That's 0.02. So that's going to be equal to our x over x naught. And remember, we said that was equal to 1 over 1 plus e. So the 0.02 is going to be equal to that. And we can make e the subject to get 49. So that's going to be the extraction factor. Now we said the extraction factor was given by Kd times V over L. We know our Kd, said it was 76 from the question. We know the L, that's the volume of the carrier, which was 50 ml, right? And now we know our E to be 49. So we can place all of that and make V the subject from this equation to get 32 ml for the volume of the solvent. Now we want to consider multiple stages. Now we are going to use the volume we had from the previous question. So the volume of solvent that we used was 32 ml. We are going to use the same thing, right? But this time for two stages. And we are assuming that we are still working with a pure solvent. So our y naught is still going to be 0. Okay. So this is stage 1. This is stage 2. Sorry, this is stage 1 and that's stage 2. So now we can look at the notations. What is leaving stage 1 now is x1, and what's leaving stage 2 is x2, right? We are assuming that there's still no miscibility and all the assumptions we made earlier. So the volume of the carrier here is going to be the same as the volume of the raffinate here, and the volume of the raffinate here as well. Now, one thing to note, the carrier here is a carrier for stage 1, and then we have here the raffinate for stage 1. But now the raffinate for stage 1 becomes the carrier for stage 2. And then this becomes the raffinate for stage 2. So we'll see why we are doing this very soon. Okay. Now what we are doing with this question is we are saying that we want to see how much separation we can bring about if we should use the same volume of solvent twice. So now in two stages. So initially when we used it for just one stage, we were able to extract 98%. So it means what was coming out here was 0.02. Now we want to see what is going to end up coming out here. So that's what we are actually coming to work on. Okay, so one thing to note is that since the flow of a carrier solution isn't changing, right? So the L is the same here, here, and here, right? And since we are using the same volume of solvent as to the previous question, so the same V here and here, and since our partition coefficient is also not going to change, it means that our Kd, our V, and our L are constant. So our E is going to be the same for both stages. So for stage 1, the Kd is the same. The partition coefficient is going to be the same for the two fluids at that pH. So the Kd is fixed. The V here is still going to be 32. The L here is still going to be 50 for stage 1. For stage 2 is the same V, 32. We said the L isn't changing, so the L for stage 2 is also going to be 50. So we'll end up having the same E that we had initially, right? And I think the answer was 49. So it will be the same value for both stages. So keep that in mind. Now, remember when we were comparing the amounts that was not extracted, the fraction was not extracted, we said it was x over x naught equal to 1 over 1 plus e from the previous question. What we did over here. Right, we are going to use that same understanding. So let me clear this screen first before I continue with that. So when we do that same thing for the stages, we'll end up having a similar expression because we're working with similar assumptions. So here, what is coming out now is x1. What was coming in was x naught. It's going to be equal to 1 over 1 plus e, right? For this point, what was coming out was x2, and what was coming in was x1. It's going to be the same thing, 1 over 1 plus e. You can verify this by actually doing the mass balance around stage 2 as we did earlier, and then simplifying this to this form. You realize you get the same thing. Okay, there's a case where it wouldn't end up being E. So I've seen a question where the volume of solvent that was coming in over here was, they're told that it's 32 here, 32 here. But you might be given a case where maybe the volume of solvent that was coming in was split into two. So instead of it to be maybe 32 and 32 coming in here, what was happening was that maybe the original amount that was coming in was 32, but we split it into two equal fractions. So we sent 16 here and sent 16 here. In that case, if I remember correctly, this will become e over 2. So you can try proving that out. But I think we'll see that as time goes on. I'll get that question for another tutorial and work that out. But that's just by the way. So what we are saying is that from what we've done so far, x1 over x naught is going to be 1 over 1 plus e. And then x over x1 is also going to be the same expression. But this is just going to be, this one over here, just comparing what was coming out to what was coming in for stage 1. And this over here is comparing what was coming out to what was coming in for stage 2. We want the overall thing. So we need to compare what was coming out overall to what was coming in initially, right? So how can we go about that? So I think this is the same what we spoke about earlier. X1 over x is equal to x over x1 is all equal to 1 over 1 plus e. But now we want to compare what was coming out overall, that's x2, over what was coming in initially. So we can do this by multiplying the two expressions. So we have x1 over x0, which we found. We can multiply this by x2 over x1. So this was for stage 1, this was for stage 2. When we multiply, the x1 can cancel out and we end up having the x2 over x0. So it means that this is going to be 1 over 1 plus e times 1 over 1 plus e for the x1 over x0 and then the x2 over x1. So in effect, our x2 over x0 is going to be equal to 1 over 1 plus e all squared. Now, we know the e was 40 now. We've already calculated that. So if we put that in here, right, we'll get x2 over x0 to be 0.004. So when it was a single stage, our x1 over x0, we had 0.02, which meant that 2% was not extracted. And that also means that if 2% was not extracted, it means that 98% of the solute in the carrier was extracted. Now we are having x2 over x0. So when we added the second stage, now we are having x2 over x0 to be equal to 0.0004, which means that 0.04%, right, was not extracted, which means 99.96% was extracted at the end, right? So yes, so that's what's happening. So we use the same amount of solvent for both stages. And the amount that was not extracted will now be this. That's against the initial 0.02. So all we are saying that at the end of the day, because we added a second stage, we're going to have more extraction. We're using the same solvents, the same flow of solvents. It was still a pure solvent. But now this time we're going to have a higher extraction, right? So when we are giving questions like this, you have to pay very, very close attention to what the question is asking you for. You see, in the first situation, we're given how much was coming out, right? And we're told to find the volume of the solvent that will be needed. In the second case, we kept the same volume of solvent, but we're told to find how much or the extent of extraction that we had. So just pay very close attention to the question. Know your symbols, and I mean always draw it out so that you won't get confused. Know the notations you are using. Be familiar with the formula and how to derive it, because the derivations are very important, and then you'll be fine. Okay, so just pay attention to what the question is asking for. Pay very, very close attention to the details in the question, and you should be okay.